How many people here are CDL people?
Oh dear.
Well, you can tell us where you are on the photograph. Right, I've nearly done. I just wanted to make one other quite minor, non-technical point. I think the 1301 was interesting from the very beginning in being a very good-looking machine. And part of the fact was, the reason for that was due to the fact that the company employed a designer to make sure that the appearance was neat and orderly and was maintained throughout the external. Noel London, his name was, and I think he did an excellent job. And the 1301 always looked a very handsome beast. The floor shape was determined pretty strictly. The front range card reader control, line printer with the card punch sticking out the front. The integrally designed paper trolley, also a Noel London artifact, out the back. Electronics down the middle, IAS here, drum control and drums there, additional drums, mag tape control if needed, and the mag tapes were the only bits that were freestanding. The little gentleman going to talk later who will tell you much more about why the layout was like so and how it came to be. So I think with that, I've done all I need to do at this stage by kicking it off, and I'll hand over next to Frank Townsend, who is going to give the first half or two-thirds of a more technical overview of the machine.
Right. Good afternoon. My name is Frank Townsend. I was Senior Engineer at the Field Engineering Headquarters of the British Tablet Machine Company. The first thing is really the genesis of the 1301. Now, the 1301 is a member of the 1300 series machines, which were second generation computers using transistors. In the 1950s, the British Tablet Machine Company, which was known as BTM, and I'll refer to it as that subsequently in this talk, was a successful punch card machine manufacturer. They had already acquired expertise in the electronic fields and produced a range of electronic calculators based on valve technology. In the computing area, they had developed a first generation computer known as the HEC, which comprised what was become the 1200 series. We've already had some discussions earlier on this afternoon exactly which is the 1200 series, but HEC stood for Hollerith Electronic Computer. Now, led by the Americans, the industry was moving ever more towards computers. Punch card installation could achieve the same results as a computer, but was slow and labour intensive. A process required many different machines with the overhead of continually moving data in the form of punch cards between various different machines. The HEC was still regarded as one machine within this overall process. The need was for an integrated data processing system based on the computer. As research and development was becoming ever more costly, BTM saw the way forward by collaboration. The initial collaboration was with an American electronics laboratory, LFE, in Boston. The result was a machine called Diana, which had a large file drum. Unfortunately, this machine was eclipsed by the announcement by IBM of Ramac, which had a larger and faster drum system. More than one other machines were also in the embryonic state. There was the 1400, known as Atlanta, and the 1301, known as the P3. BTM had the customer base but lacked experience in computing manufacturer, they lacked experience in computing electronics, so a partner was sought. GC was a well-known manufacturer in various fields of mainstream electronics, but had no computer aspirations. A collaboration was agreed between the two companies, and a joint company known as CDL was formed in the mid-1950s. The brief of CDL was to develop the 1301. Now, as GC was entering a downturn in the telephone exchange business, it had capacity at its telephone works in Coventry to assemble the final product. In 1960, CDL had completed the design principles and work started on building the prototype at Coventry. In 1961, work was completed on the prototype and it was installed at the Putney offices of what has now become ICT. ICT was formed in January 1959. This was the first of 200 machines. Machines in the 1300 series was the 1301, which was a 1-inch originally and a half-inch tape machine, and in due course the 1300, which was a 1/4-inch based version with a reduced specification, but using the same components. There was also a 1302 envisaged with an enhanced specification, including time sharing. Also, as the market dictated, paper tape input-output was added, but the machine always remained a punch card computer. Now, I'll put up this. We'll keep this in front of us for the time being. Now, the 1301, this is the specification and method of construction. The 1301 consisted of a punch card input and output. Well, one can see on here the punch card output there and the punch card input is there. There was a line printer, which is on the extreme right at the front, and in the centre was the console where the operator controlled the machine. The storage for it consisted of coarse stores for immediate access. They were actually housed in the piece sticking out to the right behind the line printer, not in the main backbone but behind it. There was a magnetic, or a basic machine had one magnetic drum. Now, magnetic drums were housed in this area here. Now, there were provision for up to 8 drums. So as if you exceeded that number, you started building them out at the back. Or rather like a sort of a Lego set being mixed together. The basic machine consisted of 1 drum. There was also magnetic tape storage. As you can see on here, the magnetic tape, the actual handlers, this is depicting unpaid ones, are freestanding, whilst the electronics for the magnetic tape yet went further out of the back there. So as we have all this lot, it's one big chunk. In effect, once it's installed, it's one big chunk of hardware which did require a room of a minimum size to locate it. Also, if you had magnetic tape, air conditioning was mandatory. Now, I'll go back to here. There was, within the arithmetic unit, there were registers. The actual arithmetic was done in a device known as the mill. And they were all integrated, as we said, in a single unit. Now, the principle behind the construction and circuitry, as I said before, GC was a partner in the project, and they had great experience in building telephone exchanges. Also, they had facilities manufacturing transistors, as well as many other electronic components. At an early stage of design, it was decided to avoid using connectors in the form of plugs and sockets, and even edge connectors, The method of connection adopted was wire wrapping. Now, I've got to possibly, I'll put this up in advance. Now the actual wire wrapping really consists, as you probably know, of wrapping a wire, literally. Normally it consists of wrapping a wire around a post. And the process of wrapping normally digs into the post and thereby gives a very good connection. In the case of the 1301, instead of having a post, in effect we had two halves of a square, let's say, two rectangles side by side, which when the wire was wrapped round, compared them, they were mechanically locked together, and we had a very good electrical contact between them. The whole, as I say, the whole concept within the machine was wrapping. It doesn't matter, if you wanted to connect something, invariably you wrapped it. There was a certain amount of, how can I put it, virtually nuts and bolts on buzz bars and things like that, but most of it was wrapping. Now, the electronic circuits, which were, I've got an example of one, were placed on a printed circuit board. I don't know whether you can see this, right? And it terminated again in a row of pins for wrapping. Now, the thing about this board is that it is hand-wired with discrete components. It is long before the days of integrated circuits and this, that, and the other. It has tracking on the back for the actual wiring. So as these printed circuit boards were placed in rows in a carrier, which was called printed board carrier. Now that picture, in actual fact, there shows, two to look at. I'll show you this other one as well.
Yes.
There you can see part of the central processor unit, and those are the printed board carriers facing us there. And this other picture, which we had up before, actually was just looking at the carrier freestanding. Now the cards were wrapped into the carrier, and the carrier was wrapped into the frame. The carrier could be connected to the carrier above or below it by further wrapping, and once you had them all in the frames were joined together by links between them wrapped, but in that case insulated with a bit of green sleeving. Now the actual, there were 27 brick positions in the horizontal row on there, and what you've got there was two racks like that making up the central part of the machine. They're back to back, so as they were known as frames, so it gave you a total of 8 of these rows, if you like, of PCBs that made up the machine. And we said there were 27 bricks within a printed board carrier. Now most of them occupied single positions, but you can possibly even see on there, sometimes if they're bulky components of them, they would occupy 2 positions. Now the actual, on the actual wrapping, we used a very simple tool. And this is actually a wire wrapping tool, which really consists of a normal pump action screwdriver, standard Yankee screwdriver, and a bit that goes in the end, replace the actual screwdriver bit, and when one when you lock this end in, what you had to do was you placed a piece of wire, wrapping wire, whether you can see it, but it was 3 1/8 inches long, and it was, I think it was 25 standard wire gauge. You place that into the machine, this device. And all in effect, you went to wrap it, was on the particular joint, in effect you're doing like that, right? The only thing is you've got to remember that you've got all these boards. Well, when you assemble the machine, you've got a wrap joint, as you say, between each pin on the board to the carrier, from each end of the carrier to the frame, between frames, up and down, this, that and the other. So there's quite a bit of wrapping, but I think I'm correct in saying I don't remember really there ever being any trouble with electrical connections. There was, as the next speaker pointed out to me, sometimes there was a problem when you unwrapped it. Watch out where the little bit goes, because when you unwrap it, you're going backwards, you're undoing the thing, and you end up with a nice little curl of wire, and if it falls in the middle, it can really create havoc. Right, so as if we move on now, actual specification, the arithmetic unit, now the clock frequency of the machine was a megahertz. This was derived from the timing tracking effect from the magnetic drum. Being reminded the fact, in actual fact, there were 2 timing tracks, the one at the top and one at the bottom of the drum, and to allow for the possibility of variation between the length of the drum, which was mounted vertically. And also there was a timing track on each drum, because if you had 8 drums, as you switch from one to the other, you've got to be able to sync your clock from one to the other. Now all movement of data within the machine was in effect Binny 10, which it ran in serial of 4 lines. Now we've been doing this in the British tab with the calculating machines before. Okay, it's a bit like hexadecimal, but it isn't. It fits in many ways well for things like sterling, because we had to remember when sterling in those days, we're not all decimal currency, and we had things like pounds, ounces, and goodness knows what else, none of the simplicity that metrication has brought us. But anyway, it was in Binny 10, there were 4 streams of 1s, 2s, 4s and 8s, everything shuffled around, 4 in parallel, so as you could say, you had a gain there, even if your clock frequency was a megacycle, but you're moving in 1 microsecond, you're moving a whole byte along, rather than a thing being in serial, which would represent 4 pulses. There were 4 highways, 2 out of the top, which we called A and B, of the registers. I wonder if did we have a... Yes, this gives us a broad idea. There you've got register A, B and C. What's represented on here, the highways you could really say, because everything moved around the machine serially, so you've got to say the highways are represented in this way, right? And you could move from register B or register C onto the appropriate highway, or register A. You've got the mill. You also had a bypass loop, which shown here for normal shifts. If you wanted to normally shift something, if you placed it in the register, you could shuffle it round and back in again. I can't see it shown on this diagram. So the arithmetic unit, we say, consisted of 3 registers, a mill, and up at the top, the CR1, 2 and 3, we had a control register. Now, being a computer, it had to have a program, and for the program to be acted on, in effect, it was placed in the control registers. The CR1 and 2 really represented 2 instructions, and CR3, you can say, really represented the next instruction address counter, which would normally be incremented. Now the size of the registers were 12 mini 10 characters, and the control registers were each 6. That allowed you 4 positions for address and 2 for function. Now, for things like Sterling, in actual fact, there was a Sterling position register, which you could, in there, define what position within your word of 12 digits, what position was occupied by pounds, shillings, and pence. Remember, particularly in those days, we had to worry about 2 10 shillings for a pound, and if you like it, 12 pennies, 1 shilling. All these sorts of things that people tend to forget now. So that was taken care of by a Sterling position register. Now the immediate access store, which might as well go back to the overall picture. Got some more, I think. Immediate access store was located in the, as we said, the rear right-hand side piece jutting up behind the line printer. It consisted of what we called gates, up to 5 gates of course store. Now each gate would actually handle 400 words of course store. The actual storage was in ferrite toroids, which were threaded obviously in such a way so as you had your read and write situation. But it was not a retentive type memory. That is to say, you had to read write the information on that basis. Now, the 400 words per gate, 5 gate, gave us 2,000 words of core store. I've got down here, that represents 12 times 4 times 2,000, which is the equivalent to 96k bits. And each core store word had 2 parity bits and 2 spare bits as well. The spare bits meant to say that if you had a failure, you always had a chance of picking one of those 2 spare lines. This is at the hardware level, to at least keep the machine going, because once you lost your 2 of your rows as such on the core store, you've had it with that, you've got to replace that particular part of it. Now the magnetic drum, there was a magnetic drum fitted up to 8 drums, as I mentioned. Each drum had the capacity of 12,000 words. It was organised into channels, each holding 200 words. And the channel was subdivided into decades, each holding 10 words, with 20 decades per channel. Access to the drum was to and from via the A register. I don't think I'll put it back up again. Remember, we have the A register is done for all things like that. The C register tended to be used for the input-output. Now the drum physically really consisted of 2 drums mounted vertically on the same shaft. Presumably it was decided at the design stage that the mass of 1 was asking a little bit too much, so they made it the mass of 2. They were aluminium drums which were coated in magnetic coating on the surface. So they ran in a vertical position at the speed of 5,240 revolutions per minute. Now each one of these cylinders had half of the total tracks, 150 tracks on each, adding up to the magic 300. As we say, as the machine ran in Binny 10, 4 tracks were required for holding word data. Everything was moved around the machine, written, stored in core store, the whole lot in Binny 10. In other words, there was always 4 of everything that was stored. Now the density, I got down here, back in density was 130 bits per inch at the drum surface. Now for drum access, there was a timing track, I mentioned that, there's one at each end. The drum enclosed in a casing, allowing the read-write head to be positioned around the drum in a spiral form. I did see you had a picture showing the drum. Amongst the transparencies. Nothing about that.
Over there.
No. Well, there are many pictures about, but I don't know whether the ones I've got here, unfortunately, wait a minute, beg your pardon, here we are. Sure it's the right way up.
Could be upside. No, I don't know.
That's the right way up, isn't it?
We'll see. Yes.
Hmm?
Yes.
Yeah, you know, it's when you get round, you know, like this, you begin to look, you begin to think.
No,
right.
there's words in the bottom actually, Frank.
Hmm?
If you just take it up a bit, the words are written on the bottom, I think.
Yeah, well, we're limited.
It says this way up. That's okay, right. That's it.
Yeah, there we are, the words, that helps. Right, now as we said, the heads were really in a spiral form, and you can see it virtually on here. Each head is a little bit lower down as you go round, spiral round this casing on the drum. Now the whole lot is enclosed. You can't actually see the drum. You would be able to if you removed the head and peered in the hole. You can see there's an odd hole there. So, but it was impossible to normally see the surface. So as an ingenious method was devised to set the head up. Now it's important that the head was set to 1/1000th of an inch, in fact, away from the surface of the drum to get optimum pickup on the head from the drum surface. And to do that, a pneumatic method was used, whereby you may notice lots of these little tubes sticking up there. They terminated at a nozzle which was a given distance from the surface of the drum. In other words, it was made relative to the gap on the actual head. And if one were to pass air down this at a certain pressure and measure the back pressure, you can measure the distance between the surface of the drum and the actual head without really seeing anything. And we had a special piece of equipment which was developed by a Sigma Instrument Company, which had a little compressor and a simple gauge on it, where we were able to position the head to within 2/10,000th of an inch of the face of the drum without actually seeing anything. So that was a slight movement away, shall we say, of this machine. Now, on input-output, we said the card input with a card reader. I'll go back again to that picture here.
Oh, yes.
The card reader is there immediately to the left of where the operator's chair is. Right? That ran at 600 cards a minute, and the cards were fed in effect, endways. You place the card, if you like, the input card on the right-hand hopper. I don't know whether you people are familiar with punch cards. Anybody never seen a punch card? So you all know what a punch card looks like then. Right, so anyway, you place those in a pile on the right-hand hopper. They were read lengthways, and built up on the left-hand hopper. Now, as we said, they ran at 600 cards a minute. Now the sensing was by photoelectric cell, which would read, if there was a hole in the card, a hole punched in the perfect position, light passed through, the cell was activated, and it read that particular digit or that particular pattern to say. There was also a method to, in effect, time the cards to maintain that that the machine knew where a particular card was at a given time. There were also things, from what I can remember, about checking, etc., but I think the following speaker will probably have something more to say on that. Now the card output, the card punch on the extreme left, that was a standard, I put it down as a modified Hollerith punch. It ran at 100 cards a minute, but underneath the covers there provided by Alarm Random, you will find a really basic Hollerith type summary punch, you see underneath there. The only difference being that instead of the punch magnets being worked electrically from relays and so forth, they were worked from power transistors in effect within the 1301. Right? And there's also a method of checking the holes punch. That again was normal standard Hollerith practice. You normally had check brushes after you punch, so as you could if you wanted to read back the pattern to make sure you punch what you thought. We move on. The outputs printing was a 600 line per minute drum printer. Now that is on the front of the right. There are 120 print positions with 50 characters per position. Now, the printed drum rotated at 900 RPM, and printing was achieved by print hammers striking a ribbon onto the paper and thence onto the drum. So as you're really like embossing backwards, if you could follow that, you had your character actually on the drum, but when the ribbon is pushed onto it by the hammer, then the imprint of the particular character appears. Now you've got to remember this was done with what we used to call hit on the fly. That is to say that that drum rotates at 900 RPM and it doesn't stop. So as you've got, when you're going to knock your ribbon and paper onto it, you require a very narrow, sharp pulse in effect to knock all three of them together and get a really sharp character. There was provision for advancing the paper between rows, either as a single or as a multi-row throw. We talk about things of sprags that were in effect 6 from what I can remember on there, and if you engaged one while this thing rotated, the paper would just shoot out. You've got to make sure that you engage and disengage at the right time. Now, the next thing is magnetic tape storage. Now, we'll talk about what we can see there at the moment. Now, the 1301 was initially supplied, said, with Ampex type TM2 magnetic tape decks. There was a standard system using 1/2 inch and a high-speed system using 1 inch. Now, the 1/2 inch system was not used in final production. At a much later time, the 1300 came along. Now, as I mentioned to you before, the 1300 was a poor man's version of the 1301, but it was the same as the 1301, but cut down. Everything was run slower, and from that point of view, also the tape was narrower. In other words, they went onto a 1/4 inch tape. And the 1/4 inch tape system was developed by Dryco, that data recording instrument company, which was an ICT subsidiary, which had been acquired again back in the, an interest had been acquired initially back in the very late 50s, because, again, the British tab realised that one thing that's missing in this country, anyway, was somebody that made tape. So as they took an interest in Dryco and eventually became a wholly owned subsidiary.
And Dave
Unfortunately-
Tyler, the technical director of Dryco, is with us this afternoon. Dave Tyler, technical
Yeah.
director of Dryco, is here this afternoon.
You're happy?
Yes, yes.
Yeah, you know, we're all talking about things that happened a long
Yeah.
time ago, really.
Yes, I went from ICT as it was then to data recording
Ah,
when they were building the
yeah,
IBM compatible.
fair enough then. Are you down on the list?
No.
No, not yet.
Right, the only pictures I've got of the Dryco type decks are in brochures, but not, we haven't got a transparency, so as perhaps after that, if anybody wants to look at a picture, they'll be no doubt around on the table. Now the console, as you can see there, was divided into two areas. Now, you imagine the brown part, you see, let's perhaps come around better. Let's say that there's this area and that area. This area was for the benefit, in effect, of the operators, the programmers, and this area was for the benefit of the engineers. And this machine was provided with a lot of comprehensive monitoring meters and switches and also an ability to change voltages and this, that and the other, purely for routine maintenance on the machine. Which was, as we said, the domain of the right-hand side, while the left-hand side, the operators area, that covered, in effect, two things. The lower row of rotary switches that you can see here were concerned with the ability to enter into any register you had selected a particular value. And you could see what was already in the register by display. In effect, these were Mini 10. There were 4 lamps in each little box that told you for each position the 1, 2, 4 and 8. The top part was the control register to allow you again to manually enter a function if you so desire to program the machine in a very arduous way, or you perhaps wanted to modify what was already there. Now I've got down now programming, the next thing I went to here. Now, initially machine code was used for programming. In the very early days, like all good computing things, and so we were not programmers were really artists. They had to really design programs. They had to consider all sorts of things that nowadays with high-level languages you all take for granted.
Can you skip programming?
Yeah.
What more have you got?
Oh, no, only about 5 minutes then. I'll rattle through the rest, right? Now, machine code was used for programming. To help users, a set of standard subroutines was developed, covering areas like input-output, mathematical routines, etc. Programs were punched on cards for input to the card reader. Now, on languages, MPL, Mnemonic Programming Language, which was an assembly level language, was available. But because the compiler was involved, it was only available for machines fitted with magnetic tape. COBOL came along.
This is covered by, this is going to be covered by Jeff. So
Is it?
Yeah,
Right.
John's covered.
Rapid write, all under.
Yes, yes.
All right then. So as the final thing here, starting the machine on a daily basis. The core store had no long-term storage ability. It was necessary to reload the machine each time it was switched on. To do this, a program known as initial orders was used. This program was punched on a deck of cards and was supplied as part of the system. To load initial orders, all that was necessary was to place the deck of cards in the card reader and press a rotary switch on a certain initial orders position and push a button. And that would cause the card reader to read in this basic program, and having got initial orders, you were then able to read anything else you so desire. Finally, just some words on maintenance. As the BTM already had a training school for engineer training. Field engineers were already familiar with the input-output devices, although the line printer broached new ground. The school was then enhanced and courses were run to cover the new area of electronics. At the time of delivering the 1301s to customers, it was ICT's policy to have an engineer located on site. He was provided with such items as an oscilloscope, etc. Also, there was a complete set of spare boards, and more than one of some types. Also, there was a complete set of discrete components. Part of an engineer's duty was to repair faulty boards, removed from the machine on site. As backup, he would have the regional specialist to call on, and the third line servicing was at FEHQ. All early machines were installed by a team from FEHQ. I think that's where I came in.
Thank you very much. Bill, do you want to supplement?
My previous employment had been with IBM at Greenock, where I had been introducing the 650. So I wasn't altogether a novice. Though it's fair to say we were introducing an American design machine and we knew very little about the design, but we knew all about the problems of engineering, change, procurement, and just getting things to go. That's a story in itself. It had its own nightmare session. But they were making them in Germany, they were making them in France, and we made them in Scotland. So I came down as a Scottish engineer with 3 years' experience of computers and joined what was called Data Handling Group in Coventry under George Gibson. One of our senior engineers in that group was Dave Tyler, who is here today, and I don't know if any others are here. I don't see them. Would I recognise them? It was 40 years ago. But we had, of course, a team. I should stress that we had a team. We were part of a group who were not really doing telephone work. We had a sister, another group just along the road, Dick Swift, I think it was called, who was doing transistorized telephone exchanges, I think some of which have actually now been installed. At that time, GTC did an awful lot of fundamental work, and nobody in UK was buying it. But there was only one customer, the post office, and they were always wanting to plan things, never buying anything. So, they were doing things, if you remember, Dave, like railway signals. We had a little railway signal, we had a little toy train running up and down the lab. We were doing railway signals using transistors. When I arrived, we were doing circuit design, so I knew of CDL, just about. I very rarely visited CDL. I say that with some feeling. Sorry, CDL, but that's it. We actually did meet Dickie Bird, and I met John Wensley playing golf one day. That was it. We met and had a game of golf. And Colin Lads was there. I don't think Dickie plays golf, and I don't think Colin Lads did either, but they must have been there for some other purpose. I've got a photograph of that if anybody wants to see Dickie playing golf. The brief was no thermionic valves, all transistors, discrete components, which you can see, mounted on a PCB, and to me, a novel experience, the printed circuit board. Prior to that, we mounted things strung between posts, I think. Turret lugs, I think, was the name of the game. And suddenly we were into printed circuits. So in the lab, we not only had to devise a circuit, we had to do the layout. But as you'll see on the boards, it wasn't all that difficult because we didn't put very many components on a board. Partly because the components were large, and also partly, but there were only the 25 pins, and you could quite quickly run out of input and output pins. You've heard about the density, etc., so I won't go into that again. The capacity of the processor was about 1,500 boards. And as somebody who had these boards in and out more than once, it's an awful lot of boards. It was huge. The registers were, of course, Eccles-Jordan circuits. This is the binary counter. Do you still call them Eccles-Jordan? Well, we did. EJs.
Yeah.
A long-tailed pair or something. There were, of course, clock pulse amplifiers. And in general, the brief was that the bricks had to be versatile. They had to do as many logic purposes as possible. Emphasis was placed on reliability. I should say great emphasis. There was redundant logic, we had error detection, we had worst case design till it was coming out our ears. We tried worst case transistors, we tried worst case resistors, worst case capacitors in all sorts of combinations and sizes. We had limit transistors supplied by a lady called Joyce Simons, who had a life testing laboratory, and she used to weed out poor looking components so that we could try them in the circuit. And we really did go to a lot of trouble, and I say that with feeling. But it was largely successful because boards did not often fail. And at that time, people would not necessarily have said that the transistor was going to be the thing we all rely on now. Honest. We also had Colin Lads in charge of us somewhere way up top, who refused to accept that any more than 3 board types were any good. He laid edicts down. There would be no more board types. That only lasted till the end of the week when another 3. And I think eventually we must have had about 50 board types. But the idea was sound. The fewer board types, the better. The better the design of the board type, the more testing went on in it. And we did not willingly put in, let's say, different types of binary. The binary counter was, the binary element was really unchanged. We might have configured it on different boards, but it was the same. The core store, I should mention, was a joke, really. It was something wonderful. You saw the unit, it's about 5 feet high, 6 feet high. There were 5, what we call barn doors. You didn't call them that in the field, obviously, but we called them barn doors, and they opened like leaves in a book, I may say. It was like 5 leaves in a book, so that you could get to the front and to the back. And the boards there were different. There are no core store boards here, but they were long, narrow ones, because the leaf in the book was only about 3 inches wide. He's thinking he's got one of these. Anyway, at the time the circuitry was done, none of us had any real experience of these things called core stores. In fact, some people didn't believe they would work. There were ferrite beads. You put about 4 wires through, or somebody put 4 wires through each ferrite bead. And if I remember rightly, they were all done by some little lassie in Portugal and brought in through Plessy, I think. Plessy were certainly the ones that got them. Well, either Malta. Some people that were used to doing lace work were the ones that did it. And we all lived in fear and trembling that we would damage one, because once it was damaged, you could not get in and repair it. Hence, the spare ones. And if you damaged the 2 spare ones, they had to go and report to somebody in town. The drum was sourced by British Tab, and I'm glad you went into all the detail in the drum, because I couldn't have. I remember there was a drum there. The physical design I will not dwell on, except that there were some novel features. The wrap joints were novel. We had a guy in the drawing office, Len Collins by name, who swore by these wrap joints. The idea was the wrapping was so tight as to form a gas-tight connection between the wire and the board, and therefore they would not decay, corrode, or whatever. And God bless him, I don't know if he's still alive, but I think he made the right decision. We certainly questioned him, believe me, more than once. And his name was called all sorts at times. They were a pain in the neck. Especially if you had to unwire them, unwrap them, do something, put them back together again. Anyway, you saw the way they were made up in the carriers, etc. But a lasting memory is that when we found a fault on the machine, and remember, I'm talking about prototype commissioning really, when we found a fault in the machine, we had to take out the carrier, take out the boards, make sure the boards went back into the same position, because we didn't want to change everything around, and it was a major headache, a major headache. We did eventually develop a sort of temporary rubbery plunge, or a rubbery thing, neoprene wouldn't it, which gave you the sort of chance of just holding a board in with this neoprene thing. Okay? That was a later development. The system configuration you've seen, and the magnetic tape thing at the back, yes. I only remember the TM2 Ampex decks. Lovely decks, lovely decks. Had pinch rollers, the tape. I don't know, you're all familiar with the problems with tape decks, I take it that you had to have vacuum chambers, the tape went in and out, and several mechanisms went bang, 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 and I don't think any of that was under transistor control. I think there must have been some power-driven gadgetry to do that.
They were called cathode type.
Right, cold cathode type drives to the... But by and large, they were good decks. Can't complain. The progress in the computer in the labs. Now I'm talking, we started, I would say we got stuck in 59. During 59 and up to the early 60s, we've been working in the lab, designing the circuitry, laying out the boards, and then eventually trying to put this logic together in a frame. Now, you've seen how it all looks, but you imagine that with a blank piece of paper and saying, where will we put the register A, I wonder? Oh, dearie me, well, let's just pick a spot, put register A in or something. And there was a lot of, I think it's called the iterative process. We were back and forward, back and forward. And the drawing office were losing patience with us, and we were losing patience with them. A lot of trial and error went on. And I would not like you to think that we just did circuitry in the lab. There were people who did logic. Reg Kilby was one. And he had a couple of people work for him. One was a young lady, and I don't think it's the young lady that's here, but we called her the Countess for reasons that those of you in the computer business will recognize from Babbage's assistant. Was she not called Countess Lovelace or something like that? Anyway, that doesn't matter. There was a little logic team working, trying to take the CDL ideas, get them into real terms, and get them into the bays. The function mesh, for instance, went into one bay, I seem to recall, and that was a work of art, getting the function mesh into one bay. There were 100 commands possible. There were 2 digits given up for function. So you had the possibility of 100 commands. And I think the programmers, whatever it is, took most of them. So there were a good number of functions. And simple functions, almost like half functions. Do this, and then go look for another instruction. Do that, and go look for another instruction. And the function mesh went into one bay, and that was really a work of art. It was shoehorned in, I think. Right, we went on to prototype testing in February 1960, and I have that on good authority because I've been given by Dave Williams a copy of my instruction to the test team dated February 1960. And we were working even then in 2 shifts, so time was catching up on us. We started at something like 6 o'clock in the morning and worked through till midnight. And that went on for over a year. Not quite round the clock. What did we do between midnight and 6 o'clock in the morning? Well, in the generosity of our hearts, we opened it up to the programmers. And Jeff, that's why he's third today. See, we never did give them priority on the machine. So some programming was done when the machine became suitable for programming, though initially, honestly, it wasn't. Some of the early things we found gave trouble. Power supplies. There was a somewhat agonizing reappraisal of the power supply situation. Almost immediately we turned this thing on. We realized that volts were appearing at one end of the machine and not getting to the far end. the gauge of wire was quite inadequate. And this really, with hindsight, of course, because I do wear glasses, you see, we've got hindsight. This is because transistors were into the low voltage, high current business. And most everybody, especially in the drawing office, has been brought up with high voltage, low current. So when we dropped 3 volts, that was half our voltage away. You know, it was that bad. So we had an urgent reappraisal, which meant the whole machine was more or less torn apart, new wiring put in, heavier wiring put in, and somebody told me just a wee while ago, the sensing as to where voltage was carried from one machine to the other, and no doubt the power supplies were boosted a wee bit to allow for this. We also ran into trouble with excessive lengths of wire. Now, originally, we didn't have any of these Wizzo programs that could tell you how much wire you were hanging on. We just hung wire on, wherever we thought. Until, oh, and I may say, with the way it was constructed, all the wiring was brought out to the front, where you then need to take it back to the thing, along the back, and out to the front again. So there was really, path lengths were unduly high. We didn't have a, as the crow flies, type wiring runs. So, of course, there was some rapid calculation done as to why the clock pulses didn't get anywhere. They disappeared into thin air. And the rules were changed, again, on the fly, you know, gosh, well, we better cut that down, and we better put an amplifier in, and we better catch that pulse in a binary somewhere and retime it and send it on its way. And a lot of that was put in afterwards. You possibly see some, no? If you see a bit of pink wiring, that was part of the change that never got. The serial, well, we talked about, or Frank talked about the card reader, yes. It was a serial card reader. So the cards were sent off, and 80 columns got shot into the machine. Whether the machine managed to capture all 80 was up to the programmer, and I'll pay tribute to them. They did a great job, because we didn't usually lose columns. It was possible, I suppose. But the card reader did not stop to say, oh, okay, feed another 3 columns. You got 80 columns, bang, or sort of bang. And the register, they were fed into register, and something must have happened, and I don't know what, but the card as read in was a standard punch card with alphabet as well as number. It was an alphanumeric card, and yet we only stored 10, 8, 4. So somebody must have been thinking somewhere. The alphabet, I think, must have been streamed off and treated as a separate entity, because the machine could handle alpha. A times A didn't mean anything, but you could read an A and you could print an A, because the printer was a 50 Ford barrel. The punch card, yes, well, we hardly ever, in the lab we hardly ever bothered getting the punch card to work. The only thing I'd say about the console, which was maybe of interest, because I saw in the write-up we were going to talk about music, there was actually a loudspeaker built into the system, a small one. And you could hear the program beating away somewhere. And it made a kind of a noise. And if you were tuned to it, and we were, of course, after a wee while, you could tell what it was doing. Or you thought you could tell what it was doing. You know, you knew when bits of the machine, bits of the processors were moving around. Now, we had a boss, and I mentioned before, George Gibson. George Gibson was exceptional, I thought. We had these 10 keys, manual keys, and George realized that he could write programs, little programs, in which he could alter the loops with the keys. So he wrote a loop for each one, and he gave each one a note. And in Christmas 1960, George played the console like it was an organ with the 10 keys and played Christmas carols. Now, I thought we might get that on tape, but I haven't found anybody's got it. Got a feeling Dave Williams has got it.
Dave Williams.
Yeah. Dave's like that, you see, that appealed to us. We were all half daft for that. We'd been at, by Christmas 1960, we'd been at it for a year. And we still hadn't got the jolly thing ready. But we could play Christmas carols. Great. And then there was the engineer's panel, yes. Did some good features, including marginal testing. We still kept thinking these components would die on us. So we used to be able to, in the morning, the engineer was told to run the test programs, and we would swing the voltages up and down and run them under marginal conditions to promote errors. Well, I mean, you don't do that anymore, do you, when you buy a little machine? We also, I seem to recall there was a thing called single shotting. You could send the program step by step, program, and maybe it's in my memory, but I woke up one morning thinking, I'm sure we could send individual clock pulses at megahertz speed. Gosh, you would have need patience of Job to get that clock through. I don't really think we ever used it, but it was there as a provision. You could actually press one at a time. And the other nightmare is we didn't have storage scopes at the time, from what I remember. We had Tektronix scopes, but things happened and we left us wondering, what was that happened? It disappeared, or it was an event, or a non-event. Anyway, by whenever, early 1961, I guess, we'd got P31, I think, ready for going down to Putney, and the programmers, of course, waiting on it, their own machine. Just to further aggravate things, somebody had the bright idea of shifting the whole lot from Telephone Works down to Stevenage. So that took us a wee while, like a few months, upset everybody. Only half the staff came down, and we had to upset the machines and start off with, we were all rehoused, and big upset. 61 was a somewhat difficult year. Bearing in mind we were late, yes, we got rid of P31, we still had P32, we took P32 down to Stevenage, where we stuck the tape on it. Now, have I got 2 minutes? I wrote this with feeling, so I'm going to tell you about it. The prototype testing really was, it strained the nerves, to say the least. We did it in 2 shifts. There was a strong possibility that work done on shift 1 would be undone by the work on shift 2. That happened. There's a strong possibility that the one shift had it in for the other shift. A notice was put on the door. Have you come with the answer, or are you part of the problem? And that, I mean, okay, part of it was good nature. None of them are here today, so I can say part of it was good nature. I was meant to be in charge of this lot, keeping the peace. Not easy. When we found an error in P31, say, but P31 was ahead of P32, but we did have them both there at one time together. When we found an error, we would correct it in a temporary way, if we could. Now, some of these errors were logic errors, like they needed to be changes made. Some were manufacturing errors, like the drawings were just wrong, and some were just component failures. But where we could, we would do a temporary fix, write it in the logbook, and send it up to the drawing office to have the drawings changed. Now, on a good day, they would change the drawings in the way that we had fixed the machine. That was on a good day. And that's where the pink wiring came in, by the way. The pink wires were to show, and we hung them on the outside so that we could tell where the changes had been done. On a good day, the night shift would come in, realise what all this pink wiring was, and get on with the next sort of step. On a bad day, the drawing office would decide not to do the change in that way, but to do it in another way, in a smarter way. So down would come some drawings, maybe at the end of a week or 10 days, which aimed to do the mod that we had been wanting them to do. The machine was generally degutted whilst any through wiring was put in, so we maybe have about 20 carrier boards out. And it would then take us something like a week to get it back on the air again, to where we thought we had been with the temporary wiring. Meanwhile, of course, since the drawings had been modified, we should have been able to make P3 2 up. That was the theory, and I suppose it worked, but on reflection, we were asking quite a lot. I'm surprised that I was as patient, or was I, at that time. All the time, of course, there were people coming up from Putney. Damn it, there were even customers being brought in. And on the day the customers were being brought in, we were told to get the covers on. The covers were never on the machine. I mean, this is great to me. I never saw covers on the machine. The covers were never on the machine. They were brought in, put on. The customers, hope there are some here, would come round and say, oh yes, you're getting on very well, yes. Of course, you are up to get drinking, so away you go. And it must have been wondering why we were so late, since progress looked as if it was so good. I don't know if this was GEC kidding on to ICT or not. Never quite knew. Didn't matter. When they went away, off came the covers, back to work again. So the need to keep up with changes was vital. It became a project in itself, was the control of engineering change. It really was quite an art in itself, getting that thing right. And I should pay tribute to the drawing office for keeping up with it. Because believe me, we were not very patient. Nobody's very patient. If you've tried to find fault and go home at, let's say, 2 o'clock in the morning, and you come in the following day at 2 o'clock, say, and it's not been done, you automatically think that they're all sitting on their backsides doing nothing. I mean, that's what night shift does to you, in a way. You think that they've got a sense of urgency. You think the whole of the rest of the factory is there waiting on you to pounce. And I should say that a part of this commissioning team did include some people from the factory, because they were desperately wanting to know what was ahead of them. They were going to be building this thing. Which leads me to my last few remarks, which are that we did in fact manufacture a GEC in Coventry. And as far as I know, the first manufactured machine went to London University in 1962, and it would be about August. I remember it went down to Bedford Square, I think it was, and it was to be used for processing A-level exam results and university entrance. And the threat was, if we didn't get it to work, there would be no university that year. So that's the kind of pressure we were put under. It's all good fun. The next one, ICT being ICT, you'll never guess where the next one went. Australia. That's just where you send your early machines. And we had a bloke went with it called Bob Sanders, and I don't know if Bob's still around. If anybody knows, shout out. Is Bob Sanders still around? But he did sterling work for us anyway. And he went out to Australia, and surprisingly enough, he came back. So he had some time convincing them that this machine worked, because at the time of sending it out, with very little application software went with it. Meanwhile, I personally was involved in shipping a P32, the P32, down to Putney Bridge early in '62 with a tape deck hanging on it, tape system. And I have a video of that going into Putney Bridge. It wasn't a video in these days, of course, it was a cine camera. But we had a little team there who were working away on that, and some of them appear in the video, so I don't see any of them here today, unless I'm wrong. Did anybody work on P32 at Putney Bridge? No. Right, and then the final thing for me on 1301 was I took over to Sweden the first tape 1301, and it went into Inchilda Bank in September '62 with a little team of field engineers, Swedish field engineers, who are just like field engineers, only even more difficult, and some people from the lab, and some programmers, in case there's any programmers here that might. So we put this thing into Inchilda Bank. It took about 6 weeks. and thinking that was it, good, we're away home. And I think actually I came home for some reason or other and was told by Colin lads, oh, by the way, there's the other bank, their rival bank. They want one too. And because you've done the one, you'll have to do the other, because there are penalty clauses like a yard long, waiting if you don't get this thing done. So we were promptly sent back out to Sweden for another 6-week session, which just finished at Christmas, 62. Now that date is ingrained in my memory. We came out just before Christmas. We saw the Christmas lights, we saw the ice in the Baltic, we saw the lot. We were perished. It was damn cold in Stockholm at winter time. Anyway, very good time. And I'll just close by that. As far as I was concerned, that was my experience with 1301 in the lab. 4 years of work, which I can, on reflection, consider was very challenging but very satisfying. And I'm very grateful to all those that helped me achieving that satisfaction. Thank you.
Thank you very much, Bill. Now, I wouldn't go so far as to say that's enough engineering, let's talk about some programming, but that's what we're in fact going to do. I'll invite Jeff Cuttle to give an overview of the software side, and then I am going to talk on my experience actually using some of the software products that Jeffrey and the team developed for us.
We'll leave that slide on.
Yes.
Right. With hindsight, the most remarkable thing about the 1301 was that it was the only software development I've ever been involved in where we had adequate time to do all the preparatory planning that we all know should be done before code is thrown onto the hardware in anger. This happy circumstance arose, of course, because of the unique manner in which the development had been organised. This has already been described, but the key factor as far as the software story is concerned was that the units responsible for the design, hardware and software development, CDL, GEC and ICT, were quite distinct companies, and the relationships between the units reflected that. Indeed, we used to take every opportunity possible to visit CDL, since for many months we were entertained on the scale afforded to external visitors, and it was quite late in the day that we were relegated to the meagre rations appropriate to mere colleagues. In practical terms, this somewhat hands-off relationship with CDL meant that, apart from occasional discussions on specific topics, we tended to get information on the system only after the design had been thoroughly worked out, so that, compared to most projects I've been involved in, there were relatively few design changes that came whilst we were in the middle of our own development. The relationship with GEC was even more remote. Effectively, we weren't allowed even the remotest whiff of hardware until they were satisfied that it was fit to expose to another company. So even in the original plans, we would have had about 18 months for software development. I can't remember now the exact timescale, and if I get dates wrong, and if I get people wrong, please correct me. But we had about 18 months, I think, in theory, and rather more than that, because of course the hardware was inevitably slightly late. That was frustrating, but it did mean that we had a lot more planning of walkthrough tests than most programmers generally do, even though they know they ought to. My own management responsibility covered all the general purpose utilities, including the notorious input-output routines, or PPFs, but it excluded languages and mathematical software. So I shall concentrate upon the aspects that I know best. But for completeness, I will first summarise what I've been able to recall with the help of some manuals that Hamish acquired on the software that I was not directly involved with. You will recall that ICT at that time was very firmly rooted through its British tabulating and parsemus origins in the business and commercial world. Despite some of the fascinating work done by adventurous scientific users such as Harwell with machines like the Treble 5 calculator, ICT really had no comprehension or interest in mathematical work other than the concern that the pounds, shillings and pence should balance. But it did recognise, looking at the competition, that computers were expected to have a mathematical capability, and it took two actions to fulfil that. First, as part of the design work they had carried out, CDL, through, I believe, Fred Durnley, had prepared a collection of scientific subroutines. I believe these were as much to demonstrate feasibility as for customer use. And of course they did not conform to the subroutine standards which we subsequently developed, and to which I shall refer later. So these returns were handed on to Charles Postle, who is here, and who will correct me if I'm wrong, and he adapted and enhanced them to the new standards, and in due course tested and prepared them for formal issue. And that, just to sort of give a flavour, is the list of contents to show that it was a comprehensive set. Judging, as far as I can recall, by the lack of subsequent problems with these, I can only conclude that either Charles did a remarkably good job, or, but not an exclusive or, remarkably few of our customers did enough scientific work to exercise them. The other mathematical venture was what ICT called MAC. Which, according to its introduction, was an autocode provided as an aid to writing mathematical or scientific programs for 1300 series computers. Only once on the title page of the manual is the acronym expanded into Manchester Autocode, but there is an acknowledgement that the source language used in the autocode was that devised by Dr. R.A. Brooker and his colleagues at the Computing Machine Laboratory, Manchester University. I cannot recall who did most of the work on Mac. Maybe you can, Charles. Doesn't matter.
Certainly somebody or the other, Jeff.
But the same comments apply, I think, as to the scientific subroutines. I just don't know how much it was used in anger. There were scientific users of the 1300 series, but like their predecessors with calculators, the 1200 series, they were a hardy and adventurous breed who enjoyed the challenge of using ICT equipment for purposes beyond its supplier's commercial comprehension. Mac was not the only language we developed for 1300. The early 60s were a fecund breeding ground for autocodes and interpreters and compilers, with every manufacturer, and indeed most adventurous programmers, creating their own unique flavour. ICT developed 3 for the 1300. The first contemporary with Mac around 1962 was TAS. One? Yes. And the 1300 assembly system. I believe Ken Barnes was primarily involved in this, but my memory is not certain. As its name suggests, TAS was close to machine code with mnemonics rather than function codes, and its primary advantage to users, the ability to treat the machine as having a single level store, thus avoiding the tedium of managing IAS, immediate access store, and the drum. The only area where there was a substantial expansion in code was in the handling of input-output, where single entries generated subroutine calls that looked after the complexity, which I shall refer to later. TAS came effectively in 3 versions. TAS 1 for small systems with only a minimum of 400 IAS, and TAS 2, which required an 800 IAS, and the tape version of TAS 3, which required 1200 IAS, and of course magnetic tape. There were other significant differences between the versions. TAS 1, as well as requiring only 400 IAS, could not use any extra even if it was there. And it also used the PPFC concept, which I shall come to later, which effectively meant that all input-output was time-shared together. TAS 2, on the other hand, could use as much IAS as the machine had available, and it used sequential input-output, with each device being handled separately. The next language was RapidWrite. Released in 1964, and I think with the same proviso in my own memory, largely the work of Ted Humby. RapidWrite was an ingenious simplification of Grace Hopper's work on COBOL, and it neatly forced the sort of free form of COBOL into a fixed field structure, resulting in one input card per statement that could be readily expanded without excessive iteration, so that it could be run on a simple card-based machine. Indeed, I'm not sure if there was ever a tape-based version of RapidWrite. I haven't so far spotted a reference to it. And I'm not sure, again, how much RapidWrite was used in anger in the real world. Which brings me to MPL, or the Mnemonic Programming Language. I associate the name Ron Phillips with MPL. Again, I'm very shaky on that. I can't lay my hands on any documentation for the first card-based load and go version of it, but I'm pretty sure it was there because, as Bill referred to it being used quite early on for development. Yes?
There definitely was a card-only version.
Right, yes, I've seen the reference, I've seen that it existed.
You had to have two passes, as I seem to remember. You did a compiling pass, and then you punched out some semi-compiled code, and then you did a consolidator run.
Right.
You did a consolidation.
That carries, yes. Like TAS, yes, the MPL2, which was released in 1964, was targeted at the tape user. Like TAS, most MPL is one-for-one with machine code, but the coding sheet, as you can see, is closer to the machine code program sheets, with a function column and an address operand, with 12 instructions per card. 12? Mm-hmm. 6. 12?
12 lines.
12 lines, 12, yes, 12 per card. And so it was closer to machine code than TAS, but less readable. It was also, I believe, more flexible than TAS, in that the tape version could manage programs that were too large to be contained on the drum by breaking them into sectors. And it could also handle both the PPFC concept of doing all the input-output together, and also the serial concept, which is more effective, where long bursts of a single peripheral are required. As I've said, I was not responsible for the language developments and can't go into much further detail on them. One point that impressed me when I looked at the language manuals to prepare for this talk was that all of them provided facilities to include subroutines from the 1300 library, and the consistent way in which this could be achieved in very different languages is a tribute to the work that was done by the team that did in fact report to me in establishing that library and the rules for its use. just as an example of a typical subroutine. One of the main reasons for the strength of the subroutine library was, I think, the long period that we initially had with a well-defined design and no machine to run software on. So we had ample time to work out a sound set of rules for the library, to write lots of little routines, and this is all contained on that one program sheet, and to check them out by hand. And in the process, we steadily refined the rules, and at least for the shorter routines, had a library that was substantially tested before it ever smelt a hot transistor. Whether the library met the customer's needs was another matter, as of course over this period there were no customers, and we had to guess what they would want. Again, judging by feedback when delivery started, we would appear to have got the selection reasonably right, but I was occasionally haunted by the thought that maybe the reason most of the routines never got too many bug reports might be merely that nobody found the slightest use for them. And I was always pleasantly surprised when I visited customers for some other reason to discover that they did actually use quite a lot of our goodies. When eventually the first machine became available, only overnight of course, as Bill has said, at Coventry, we feverishly allocated time slots and drove furiously up and down at the newly opened M1. I think there were no speed limits then, and bearing our precious packs of program cards. With hindsight, I'm grateful that the traffic levels were so much less than they are today. I'm sure that otherwise tired programmers speeding back after an all-night testing session would have been a serious accident risk, and as a manager responsible for dispatching them, I would have had a very real worry. The testing itself, for the shorter routines, went well as it was easy to one-shot, as Bill has described, and view progress on the console. And because of the long delay, we had got plenty of test data that we produced. The logical fallacy, of course, was that we had already hand-tested against that same data, so that we were still liable to miss any obscure bugs that we had not already anticipated. But that's a fact of programming life. Of the general library routines, I think it was only a few large ones that caused real problems at this stage. PAYE springs to mind. The story was very different for the input-output routines. Which brings me to the PPFs, always the most dramatic aspect of 1300 software, and one which featured heavily in courses on technical presentations at the time, even though, once the PPFs worked, the normal programmer never had to do much more than make a subroutine call, and all the arcane mysteries were below the surface. So why were the PPFs so popular with the punters? The answer, of course, was first that they represented a real departure from previous practice, and second, that although the programming problem was a substantial and complex one in relation to the technology of the time, the nature of the problem could be explained to and comprehended by non-programmers, and salesmen and customers delighted in the insight they perceived into an arcane world. So for those same reasons, it's a highly appropriate aspect of 1300 software to concentrate upon for the rest of the talk today. The PPF, print, punch, feed concept arose because the designers realized that they had got a processor faster than anything they had enjoyed before, and that one of the ways that they could get value from that speed was to cut out some of the hardware costs elsewhere in the system. There's that beautiful. What's your slide of there? Oh, there. Further, unlike previous and competitive machines, where the input and output peripherals were all separate units, connected by fat cables to the main system, in the 1301 it was designed as an integrated system, with, as has been described, and as you can see there, the reader, printer and punch all under the same covers. Was it Estrie and Brazil? Was that the...
Estrie and Brazil.
Yes, Estrie and Brazil. And all looking as though they're totally integrated. Of course, underneath, I think they're largely connected by just the same old fat cables.
No, these blessed wires with wire wraps all over the place.
But still, they were discrete units.
There were certainly discrete units. There was possibly a cable went to the punch. I can't recall, but there was a cable went somewhere. But
It had been a punch, yes, it would be, yes. This combination of integration of processor speed provided the opportunity to take much of the cumbersome electromechanicals out of the peripherals and replace them by software that just provided the critical signals needed to read or punch a hole or to print a character. The snare, of course, was that they were all still mechanical devices, taking time to speed up and then churning relentlessly at a fixed speed or vaguely fixed speed until they were slowly stopped. So once the card read was initiated, the reader threw 48 bits at the processor for every 6 columns, and if the processor didn't catch them at the right moment, the whole read failed. Conversely to punch, 80 bits had to be thrown 12 times at the punch at just the right moment, actually 2 lots of 40 bits, at just the right moment to catch the card as it was passing under the punch position. And for the printer, with 50 characters round the print wheel, in 10 sections of 5 characters, and 3 banks of 40 character positions across, had to be directed 50 times, once for each character, to catch the print wheel as it went round for every line. And it'd be in between lines to send commands to raise or lower the infamous sprags that controlled the spacing. No talk on 1300 would be complete without reference to the sprags. In practice, they were one of the least of the programmer's problems, but they captured the imagination, and they illustrated perfectly the manner in which software could control mechanical hardware. And they could readily be illustrated to customers with a cardboard mock-up that I developed. This is not the original, but it's as near as I can get to it. Actually, it's the only bit of hardware I've ever developed. So again, I had to bring it here today. The original was in much heavier duty corrugated cardboard, and people could come and play with it and really make it click round. The paper feed, Sprag concept was rather like a clock escape mechanism. The paper feed mechanism was connected to a cog with 5 teeth. I believe, actually, having looked at one of the manuals which I hadn't seen before, they were more sloping than sticking out like that, but the principle is the same. And there were 6 sprags which could be raised or lowered. And at any one time, one of those was lowered and engaged against one of the teeth. Lowering an adjacent sprag, and then raising that one, allowed it to move round 1/30th of a revolution, which was 1 line. And you could also see how you could lower other sprags and move up to 5 lines at one time by making the right selection. The computation of the appropriate sprags to operate at any time for a given number of lines was trivial, but the sort of thing, again, that a salesman or customer could understand and think about and see how it all ticked. There was a belief, probably mythical, that if all the sprags were lifted together, the mechanism would revolve so fast that when any one sprag was then dropped, it would immediately be broken. And accordingly, I provided my model with a spare sprag neatly wrapped in a cellophane package. I think that's probably enough of that, but I couldn't resist it. You can play with it afterwards.
Jeff, can I just interject there that there was actually an order which said lift all sprags?
Yeah.
Yes.
Yeah.
Yes. Yes, I.
It was really
You threw.
thrown reasonably.
The
Yes,
paper went
that's
off.
right. That's right. And
Could
I
you-
have a feeling that at the time when I actually developed the model, which was right at the very first courses we did, we hadn't even got to the complete order code. But though the sprag mechanism provided a good illustration of the use of software to replace hardware, it was in fact the multiplicity of reading, punching and character printing signals that created the problem for the PPF developers. The card reader ran at 600 cards a minute, equivalent to 140 chunks of 6 characters of 48 bits per second. The punch at 100 cards a minute, or 20 rows, each of 2 banks of 40 bits per second. And the printer at 600 lines a minute, or 500 character positions a second. So to operate all 3 together, the PPF had to deliver 1,680 precisely timed signals, totaling 68,320 bits per second. I think, if I got my arithmetic right. When you recollect that it also took 7 cycles to process a single word of IAS, and that the 3 peripherals operated asynchronously and timed by different and by no means constant electric motors, then you begin to realize that the apparently phenomenal megacycle clock speed was actually being stretched to its limits to keep this whole sort of vibrating merry-go-round happy. We're accustomed today to complex multi-threading processes, but never do we have such tight time constraints in relation to clock speed of the day, nor the limitation of having to keep the entire code and its data within the 400-word IAS of the entry-level machines. One other thing which but Bill brought up, sort of how the data was presented. I said that it was typically done in banks of 40 bits. Of course, the machine was not a bit machine. So to present a bank of 40 bits, these were distributed into the 1, 2, 4, and 8 character positions of register C, so that it was presented as 10 characters rather than 10 binary digits, rather than as 40 bits. And arithmetic work had to be done to create it in that form. And the question about reading a column of the card which could contain a character was translated into 2 binary digits. So that was how that was handled. The programmers who lived with the PPF for several grueling years were Rex Bowman and John O'Keefe. And the credit for its success, which was just as critical to the success of the entire system, rests entirely with them. Undoubtedly, the worst period was the first few weeks of testing. Unlike any of the other subroutines, it was not possible to simulate completely the operation of the PPF on paper, as one just could not recreate the arbitrary asynchronous demands of the different peripherals. More seriously, even when a real machine was available, one could not apply any of the standard debugging techniques of the day, because you cannot one-shot a time-critical program, nor can you insert little debugging bits of code without upsetting the balance. All you can do, if it doesn't work, is guess, tinker, and try again. For night after night, Rex, John, or both would drive up to Coventry, and for night after night, their precious PPF, on which they'd expended years of intellectual effort, just did nothing. Each night they would phone back, and we all despaired with them. Now, like all programmers, as they had worked on the first program, they had from time to time come up with new ideas that they would have liked to introduce, but could not, because it would have meant substantially changing code that they had already carefully hand-checked. Well aware of the Hartree constant and its varied causes, I had not permitted them to carry out any such retrospective tinkering. But I had agreed that they could hack together a Mark II version, the PPF, in their spare time to incorporate all these ideas so as to provide the basis for an improved successor product once we got the first desperately needed version into a usable shape. One night I had the usual weary phone call, still absolutely no signs of progress, and the despair was so evident in their voices that, purely to give them a break, I suggested that they put their hacked up Mark II version onto the machine if they happened to have it with them. 10 minutes later they rang back. It was working. Not completely, of course, but enough that they could get into serious and sensible testing. They'd never touched Mark I again, and from then on the PPF prospered. I'm sure there's a moral to all this, but I never know what it was. Later the PPF was expanded into a PPF-T to allow magnetic tape to be controlled at the same time. This is not actually as difficult as it sounds, since although the tape units at 22.5 or 90 kilocycles a second had comparable or higher throughputs than the card reader or printer, they were far less demanding in their commands and timing. With hindsight, the all-singing, all-dancing PPFs were never as critical as they were originally thought to be. The practical difficulty was that they only delivered their best if you happened to want to read 6 cards at the same time as printing 6 lines and punching 1 card, or multiples of that. Real life is not actually like that, and for the majority of applications, it was just as efficient and far easier to do spurts of one activity at a time, doing a little bit of housekeeping in parallel, and the separate serial, print, punch, and feed routines that John and Rex also developed were probably used much more than the glamorous PPF in practice. Nevertheless, it was a breakthrough, and although I have subsequently encountered software that was far, far more clever and much more complex, I've never met anything that was so close to the edge of viability in its time criticality and memory constraints. Looking back on the entire 1300 software today, with today's eyes, and especially when I looked at the manuals, I am impressed by the consistency of what we achieved. The languages, the subroutines, and the PPFs all knit together in a surprisingly well-coordinated fashion. And this was especially remarkable when you remember that it was done at a time when there were no generally recognized programming rules in existence, when we all felt that we were pioneers and we gloried in opportunities to do our own peculiar things. The reason, as I said at the start, was that the 1300 was one of those rare software developments when we had more time than we thought we wanted for planning and desk checking. And it was only after we had more than completed those tasks that we had access to Bill's real machine. The pressures started then, of course, but were undoubtedly less than they would have been without all that careful preparation. And without that spare time, John and Rex would never have had the leisure to hack together PPF Mark II, and their sleepless ghosts would probably still be haunting Coventry night after night, trying to make the beastly thing work. Thank you.
Yeah, well done.
A few words about a couple of contrasting applications. PERT, the Program Evaluation and Review Technique, and a marvelous thing called the ICT serial. PERT, or Network Analysis, was introduced to me, certainly, as a young programmer in Putney Bridge, I suppose very soon after the first real 1301s had come down there, was introduced to me by a magnificent film that had originated in the Pentagon. and it showed this marvelous new program evaluation and review technique being introduced to some top brass of the American forces. And when you've seen an audience of American admirals looking pugnacious, by Jove, they look pugnacious. The sort of thing we were working on was analysing networks of activities, joining events, and finding out how long the job was going to take overall, and which bits of it were critical, and so forth. And that's a very simple test network used for trying out our programs on. Each activity was allowed 3 time estimates, pessimistic, most likely, and optimistic, and we got a reasoned average out of those by adding together 1 time the pessimistic plus 4 times the most likely plus 1 times the optimistic and dividing by 6. That, you see, to me as a classicist, that seemed clever. I think it's quite interesting that really very early on in the life of a machine like the 1301, we were developing applications which had this overall structure. On an input run, all the input data, the events, the analyses, and so forth came in from cards, verified, and ultimately came out onto a carry-forward tape. And on subsequent runs, that tape formed part of the input, plus cards recording activities that have been completed, events that have been achieved, and so forth, activity durations have been modified, and the thing cycled around very nicely. I joined the project at this time when the input phase of the program had been written by a very, very bright and charming young man called John O'Rourke, who was tragically killed shortly afterwards in a car crash, not his fault. And the input module did these elementary activities. All the data went out to tape as a means of preventing the IAS, or even more, the drum, being cluttered up with event descriptions, activity descriptions, which with long strings of alpha you didn't need to hold internally. The activities were reduced to 2-word records and events to 3-word records. And those were stored on the drum. Both the drum stub records and the large-scale records were sorted, sort on drum and sort on tape, and the events were pseudo-numbered. And John, having done all that, I arrived with a precise specification of what I would find on the drum in order to write the central time analysis module. And this was fun. Going up to the drum, getting the appropriate chunk of the stub records, going through all the activity, expected times, creating activity variances. Can't remember the detail of what that meant, but it's obvious in general sense. And from that, working out when, clocking up activity times, getting the event earliest times, and again the event variances. And then we're doing it all in reverse, just to get the event latest times, and then having done that, to squirt the results out to tape. Kept me out of mischief, and most of the time out of the 8 bells. And quite enjoyable it was. And it was nice actually having a machine there to test it on. The output side of the program initially just produced a series of lists, and again John O'Rourke was responsible for these and did a very good job. Subsequently, lots of other things came on. There was a separate freestanding bar chart program to take the same analysed network and produce a variety of bar charts from it. And the whole package of programs went through successive modifications. The first generation that I was involved in, we were only looking at analysing things very simply by time. Then it very quickly became apparent this is not necessarily the only thing you need to do, because if a time analysis says that in week 1 you need no bricklayers at all, in week 2 you need 75, and in week 3 you need 5, that perhaps is another way of optimising it. So the ability to smooth resources and impose ceilings of resources came on afterwards. But a very successful programme altogether. I was proud of my little bit of it. And it was largely converted, straight conversion into 1900 code, when 1900 came along a few years later. And on 1900 it had a very respectable and long life. Here's a form we haven't seen so far. Operating instructions to the console operators. Load the work tapes, load write initial labels to the tapes on decks 1, 2 and 3, and also to a spare work tape. Load the program tape on deck 5 without a writing ring. Cards into reader, line up the paper to print 1 centimetre from the top of the page. Subtlety. And then step 1, IOs and start. IOs, initial orders and start alongside it. And at the end of that, the standard stop appearing in the control console was 111111. Fairly conclusive when you've got to it. Start again to do the job setup. And again, specifying what stop should appear in the indicators. Set switch 25, manual switch 25, and start, and so forth. And down at the bottom, carefully, all the error stops that might occur under various conditions, and what the operator was supposed to do when it happened. Mark the stop on the rejected card and press start was the main thing. That little program on a modest machine with one 12,000 word drum and 1,200 words of IAS would handle 2,000 events and nearly 2,500 activities. So it's quite respectable numbers. That was how it should have been done. By contrast, the next project that I was involved in, the ICT serial, had all sorts of things wrong with it, but those didn't appear till later. The serial was an in-house term for the program which controlled all manufacturing activities. So how many tabulators we want built in March, in period 6, and so forth, all the way through the year. And there was a great deal of pseudoscience built into this program. So we knew, in theory, how long it would take to build a machine from scratch, how long it would take to rebuild a machine that had been withdrawn from one customer and was going out to another. Because, of course, in the days of BTM, the punch card machines largely operated were dealt with on a rental basis. So machines went out and came back and went out and came back. There were refurbished times, specified according to the amount of flash and the type of wet cloth you cleaned them with. We built in what stock there was. We built in orders. And God, we built in forecasts. Forecasts of sales and forecasts of machines that were going to be withdrawn. And for the processing, aggregated all the inputs, shuffled them in a scientific manner, and made the output look nice by smoothing it by polynomial interpolation. I include that phrase because it is, you can see that it is stuck in my memory. I could deal you an ablative absolute to this day, but smoothing by polynomial interpolation, I haven't a clue what it means. I just know I did it once. And we output for each machine type the manufacturing program, the rebuild program, and the refurbishment program. And in an ideal world, it might have made sense. There were some positive points about this. It was written in Mac, which I found congenial. And I didn't actually have to do very much writing, because to a very large extent, the specification of the program, which was produced by, we'll call him a genius, called Frank Ellison, the specification of the program was also written in Mac. So my part in the exercise was largely to translate Frank's specification from plain paper onto coding sheets. And this I seem to achieve with reasonable success. But another interesting bit was that we found that the data was subject to continual change, adjustment, resubmitting. And we were having to resubmit this run very frequently. And the actual, the Mac compiler or interpreter, the software that it was running on, was itself about half a card tray of cards. And those took some time to read in and sort out. And then the program had to follow behind the assembler, and then the data had to follow behind the program. And the actual running of the program tended to be truncated because we'd come to the end of our slot. A high proportion of our slot had been taken up by these preliminary software housekeeping activities. So we had the great fun of cutting out those preliminary stages by preserving the program once it had been assembled, compiled, installed, and then writing it out separately to mag tape. And this was actually quite fun, working out how to do this, where you could interpose in the logical stream and get in to shove your program out onto mag tape, and then what you could do at the other end to suck it off mag tape, put it on the drum, and then revert to the normal stage of pulling tracks down off the drum and obeying and so on. So that was a good bit of experience. The negative side, Helen, really did outweigh those. Starting with untrustworthy forecasts. Though I do suppose I derive one benefit from this experience, in that I will never trust a salesman's forecast. Not unless his bonus entitlement is linked to the accuracy of his forecast, and I've never met a salesman who would sign up to such a bonus scheme in the first place. So the forecasts were appalling. In particular, the forecasts of withdrawals, because withdrawals always meant, in theory, a reduction in the salesman's bonus, because it was reducing the amount of machines for whose installation he had been responsible. So he didn't like forecasting withdrawals. It's also the specification concentrated on producing the perfect manufacturing program for this model of tabulator, then for that model of reproducer, then for this model of sorter. And it simply didn't take account of the fact that the world was changing. And we were now starting to look at systems having configurations, and that these needed to be scheduled in logical synchronization. And that it wasn't any longer sensible to talk about the number of tape decks, say, as an independent, arbitrary figure. We needed to talk about what are the incidence rates of tape decks on typical systems, and how did incidences change? What was the system development profile? all those new ideas were coming in, and the man who in Putney was in current planning department actually did the serial by a combination of guile, long experience, and common sense. Henry Harnack, he was devising the changes to his rules that would be required to cope with this, while we were pootling away in this logical stratosphere, having fun, but not producing anything that had advanced the company at all. So that's all I need to say about 2 episodes out of my life as a programmer aged slightly more than 13 3/4.
Well done.
And now we're coming much closer to the present day. I'm going to hand over to Stuart Fife, who had, I think, a jolly time with a couple of 1301s and can tell us what happened at a later stage in the history of the machine.
Good afternoon. I was sharing a flat over a shop with a couple of other students in Surbiton for Kingston Polytechnic in the early 70s. We did a lot of weird stuff, like the electric toilet flush that signalled the world when it was being used and could be operated remotely for giving surprises. And there was a Meccano rover that ran up and down the pavement of the street just outside the flat, alarming people at the bus stop. We thought it would be fun to buy a scrap computer to play with and let schools, researchers and ordinary people just come and use it for their own projects. At that time, the Amateur Computer Club was among the few national groups pursuing this new strange hobby. They published hardware designs, and I'd already made an adding machine using old Stroger telephone parts, but wanted something better to really use. We wanted to link it by telephone to an amateur astronomical observatory with a big telescope near Croydon. We looked at Elliott 802 with mercury delay lines and a PDP Watsit and got to know the surplus electronics trade and the world of 5-track paper tape, but nothing was quite right, not a proper machine. It was a surprise when I had a phone call and a visit from Rodney Brown, an ICL engineer, who said that London University would be scrapping a machine to replace it with a 1904. It was in their administration building, Senate House. Rodney said that it was a bit big, but had everything necessary and there's scope for adding attachments of our own. Just the job. A bit big, wow.
Right.
We visited Senate House and saw Flossie in action, and it's the 1904s in the background in the next room. Apparently, this was indeed serial number 6, which they got in, we learned today, 1962. And it had the first commercial type tabulating printer. The previous things hadn't been remotely comparable, so a nice machine. I think my GCE pass slips were printed by it, as perhaps were some of yours. It was in fact the programmable tabulator that Babbage wanted. Apparently we were only competing with scrap dealers for the price of the metal, and the operations manager, Mr. Hutt, was pleased to see it going for educational use at a price of £200. We spent a few days camping in his basement while we dismantled it. Engineering students seem to enjoy this sort of thing, very odd. We studied the manuals and knew more or less what we were doing by then, with help from friendly ICL engineers. The units come apart very easily after cutting the wire straps between the bays and unbolting the frames. And it's all on wheels, which is a very civilised arrangement.
Yeah.
There's a lot of ironmongery for the kick plates and covers, so we took photos to help the process of reassembly. We didn't know how long it might be before it could be turned on again. In the event, it was a couple of years. Well, in 1970, we had nowhere to put such a thing, of course, and had to find a temporary store while we looked for permanent premises. There were a dozen friends helping, and we strapped the units into a big lorry and took it to a double garage in Sutton, where a colleague, Trevor Jarrett, was living, or in the house. The last I heard of him, he was selling computers from ICL in Australia. It was a tight squeeze, and there was a small heater to discourage condensation. That house and garage has been demolished now. It's just across the road from where Harry Seacombe lived. I won't describe the tortuous search for premises, but we had noticed that estates of wartime prefabs were being dismantled. You could get one of these for £200 delivered in sections. It suddenly dawned on us there was room for just enough space in the back garden of our student flat for one of these. Provided we bought the lease and pulled down 2 derelict workshops, arranged planning consent and borrowed a couple of lorry loads of concrete down a narrow passageway that was the only street access. The best part was a party for all our helpers and friends in the empty room. The council made us add an internal brick wall for soundproofing, and there was a lot of fuss about whether there was really 3-phase mains outside. All went down that little doorway. The first power on was not a success. No smoke, but the clock wavefall was all over the place. This derives roughly from just amplifying a drum track. We wanted to load some test programs using an engineer's trick whereby the card punch can be used as a card reader, since it incorporates check reading stations that's normally used to verify the correct punching of holes. What I've done is Mr. Finch, also Mr. Finch. Never mind. Go on to Ryan with the card punch. The card punch made a horrid noise and jammed because the motor was rotating in the wrong direction. All the motors were rotating in the wrong direction, including the drum. The 3-phase mains was wrongly connected somewhere, although the colour sequence appeared right. The fault was probably in the street, but easily fixed by swapping a couple of phases. That fixed the clock, and now we just had to find where the faulty circuit boards might be and anything else that wasn't working. Fault finding was pretty easy because there were test points everywhere. In fact, it's all test points. The diagrams are faultless and identify every pin and wire, and the test programs are pretty good at identifying the problem areas. A measure of ingenuity and imagination is still needed to translate the initial symptoms into which gate or board is faulty. And for me, that satisfying process of deduction was what made the project so worthwhile, along with the things we used it for. With multiple faults masking each other, it did take some months to commission the machine. I remember the mechanical timing adjustments on the printer were particularly tedious. It was Derek adjusting the printer. But once it had settled down, there was a fresh fault only about once a month. The blue sections of the panels contain engineer's controls. On the main console, the engineer's section monitors the internal state of subsystems like the DTU and all the power supplies. And from there, the power voltages can be varied up or down in an attempt to provoke faulty behaviour before it becomes a problem in normal use. Some sections were quite a puzzle because it didn't go wrong often enough to let us become fully familiar with the circuitry. It could take a day to pin down a subtle fault in the tape system, but we would learn a lot by the end of it. An oscilloscope and voltmeter were the test tools. DC and 1 MHz are easy to measure. An operator sitting at the console will send specific signals, data values, or operations to most parts of the machine, and the effects be monitored on the gates by a colleague wheeling round this enormous oscilloscope from bay to bay. Sitting with diagrams open at the console, one would call out things like, see if 8G275 goes high when I clear CR2, and then power off and whip out the faulty card. By now we'd formed the Galdor Company Brackets Electronics Limited, trading as Galdor Computing. My colleagues Andy Keane, Derek O'Dell and myself were studying electrical and electronic engineering, which included light and heavy current studies, which seemed quite appropriate. Others came to our flat or lived nearby, notably Dirk Koopman, Don Hedges, Chris Hewitt and later Peter Singleton and John Skeen. The name Galdor is a character in a book that I was reading, Lord of the Rings by J.R.R. Tolkien, which was required reading for students. A funny thing, we asked for an ordinary telephone line, and without prompting, the number we were given was 399 1300. I took this as a sign we were doing something right. Moving the machine to Surbiton with another tower lift lorry, we're going back, this is the missing page, was easy enough, except that one unit was too wide to go through the passageway.
Yeah.
So we got out a hacksaw and attacked some runner extensions. These runners have to be temporarily attached to the main console to stop it falling over on its face.
Yeah.
That was done outside on the pavement in the main shopping street at midnight. The most time-consuming part of reinstallation was, of course, reconnecting thousands of wrapped wire links between the bays. We made a jig and manufactured pre-formed links in 3 sizes with insulated wire, and instead of wrap joints, we soldered them. And they were colour-coded. They're all green. We discovered that some corners are best connected by a left-handed person and others by right-handed. There's no risk of making a wrong connection. It's all one-to-one links. The design is ideal. It's a lovely machine to work on. Instead of the standard inline arrangement with printer and console, we angled the printer backwards about 45 degrees to make it fit in the building. The triangle that this opened up allowed a convenient extension to the console work surface. Having wire wraps everywhere certainly slows down fault finding and maintenance. It is generally worth making some additional tests to confirm where the fault is before actually taking boards out. There are rubber strips with a row of holes that hold a card in place temporarily for testing, called quick wraps. This is an ideal engineer-friendly scale of machine. We replaced individual 40 transistors when there were no spare circuit boards of the right type. You couldn't do that with integrated circuits or TTL logic. The mechanical parts are nice to work on too, being well made with heavy castings and oil-filled gearboxes. Lovely stuff. Having unbuffered peripherals is annoying, but it does keep the price down. The main program has to loop and wait for the printer barrel to rotate to the next letter you want to print. This can be concealed in modular routines, but is hardly efficient. It was quite a marvel that it works at all, as evidenced by the measures taken to achieve the clock rate of 1 MHz. The many capacitors and coils that populate the circuit cards are there to help these specks of germanium switch at these speeds. And to switch reliably, even when they're attached to maybe 20 feet of wiring. Apart from what came with the machine, spare parts came from dismantling other 1300 series wherever we could find them, with our troop of friends and a big lorry. As the machines approached the end of their life, maintenance must have suffered, for we saw a lot of quick wraps in place permanently. There was one machine in Bridgewater and a multitasking 1302 near Hastings with 1-inch tapes. Another was at the office of the official receiver on, I think, Millbank, where we were told a bomb on the window ledge did nothing more than dent a panel, and where security had insisted on watching while a drum that needed changing was dismantled and the magnetic oxide washed off, just in case it contained any sensitive information. In this way, we were able to bring it up to 6 half-inch mag tape drives, and of course the full complement of core store, and add a couple of extra drums. The additional tapes were useful. We could keep a library of the commonly used programs on one of the tape drives to call on when needed instead of loading from cards all the time. A full set of spares was put by, and we swapped the card reader with a spare one when we were unable to keep the original running. We added 8-track paper tape, reader and punch, and picked up a variety of punch card preparation machines and Verifier with real keyboards instead of a finger dance. Parts get all over the place. The BBC props department used to have a console. It turns up in Doctor Who occasionally. Modifications are easy to make on the 1301. There are gaps in the instruction codes that can be used. You just have to add some gates to decode the instructions and do something interesting. An approved modification, called the black box, involved installing several racks of boards and lets it drive a 1900 series tape deck. This was used to help systems that were converting their data. One of these was in Glasgow and had 1/4-inch tapes and involved a 2-stage transfer. The famous Sterling arithmetic instructions are achieved by messing about with the carry of overflows from one digit to the next, as indeed are decimal instructions. Since the national currency had been decimated, the Sterling instructions were redundant, and we made alterations to the mill to treat those commands as plain 48-bit binary. It's all documented and can revert to Sterling just by operating the switch in one of the bands. One practical change was adding some buttons on the console to clear an entire register in one go without having to dial up a load of zeros first. This involved attaching diodes to the back of the dials to form simple pull-up gates. Some changes were made to the original fixed program initial orders. This lets the operator set some manual indicators to do things like unload all the tapes. And a very big help was our invention of the G card. When a program is being loaded from punch card, the last card that's read is normally an E or entry card, whereupon the processor stops and displays all the ones in CR1, waiting for the operator to set the program running. Well, if you overpunch the card's E with a G, it gets read as a G, and the modified initial orders doesn't stop, but runs the program at once. This can save a lot of time to run a series of programs in sequence unattended. It works because G has a numeric of 7, which masks the 5 of the E in binary. My colleague Andy Keat, here today, can take credit for much of this sort of trickery. We added an electric typewriter and keyboard of sorts. This was used to do simple things like show the label details of a magnetic tape. The interface for this device used TTL logic, which has compatible voltages but a positive ground, so we had to build it upside down and floating to attach it to the 1301. The processor stops when it needs to tell you something, and we weren't going to stand over it all the time, so we ran a line up to the house, isolated with a relay to flash lights whenever it was lonely and needed attention. I wanted to get it to control the model train that ran round our flat. It got quite hot sometimes, and I also wanted to add an instruction that could be triggered by temperature to release the doors and flap them about a bit. As it was, we fitted a chimney or two in the central units and a big extractor fan in the roof space. The commercial 3-phase electricity tariff gave us cheap power, but only overnight. A nocturnal lifestyle suited us, but confused our clients. We had occasional visits from the Amateur Computer Club and a few schools, but most of the activity was with customers who appreciated our low overheads. We wrote programs to look after club and society membership lists. It was called ClubSoc, and used by some 35 organisations eventually. Nowadays they do it all themselves with PCs, but in the mid-70s a cheap Euro service was ideal. It started with London Village and went on to include the UK administration sections of of Amnesty International and Friends of the Earth, Town and Country Planning Association, National Council for Civil Liberties, Legalise Cannabis Campaign, Vol magazine, to name just a few. The data was punched onto cards by a separate bureau, and we will produce lists and mail-out labels. We also printed biorhythm charts for a client, and later on processed the complex administration for Southern Counties cat fanciers shows. An attempt was made to generate schools' timetables by machine, but the complexities of split sites and individual pupils' requirements meant that this project was not a real success. The programs are written in machine code and assembler. The relativized loader is an excellent way to combine separate modules and was a good training in how language compilers ultimately work. We adapted the assembler to use symbolic names and comments. Having self-modifying code is fine and wonderfully efficient while the programmer is in full control, but wouldn't work now in multi-threaded systems. We provided standby processing for other ICL sites and did a 6-month period of continuous contract operating in 2 12-hour shifts at Liverpool Victoria Friendly Society. Their machines were Samantha and Arthur, which suffered a Y2K crisis when insurance rates went over 10%, suddenly needing 2 digits. We used the G card and persuaded them that initial orders had always had visibility. We did enough like this to keep the business running and kept on buying scrap machines, progressing through the 1900 series, which contained useful amounts of reclaimable gold. We used COBOL and George 3 and moved to bigger premises. I left Galdor when the fun went out of it, and now I provide software support for vets. And I'm looking for more work if anyone's listening. In conclusion, the 1300 is of a size where I feel it's just possible that one could get to know everything about it, hardware and software.
Yeah.
Somehow that's important. It feels uncomfortable with modern PCs and stuff where one only has the roughest idea what it's up to. I can see in the audience several other people from Galdor. Perhaps they can fill us in with anything that I've missed. We handed on the machine when space was needed for other things, and the next speaker can take up the story. Working around Flossie was one of the most satisfying things I've done. Much credit goes to the designers.
Roger Holmes comes in. Roger, do you need the... No. Right.
We've done these things back in the 60s. Period. Here it comes. Yep. Oh, yes, he's gone. It's got low and turned itself off. Okay. Let's reboot it. Anyway, while it's doing that, right, my name's Roger Holmes. Well, I guess you think I'm a bit young to be, I'm not very young, but to be talking about 1301s, but yeah, couple of minutes. Right.
Little bits of housekeeping to I hope if you're interested you will have seen
Got a memory leak there. Prototype software. Yes. Okay, right. Right, anyway, saying I'm not really old enough, but I was much younger when I was first involved with hardware.
but it was actually nuts and bolts and screws and things in my father's shop. First contact with computer hardware was in the lower sixth at school. As part of a general studies course, we took a 5-mile trip one afternoon a week to Erith Tech, where they had an 026 and an 029 key punch. There we learnt Fortran 4 and one-finger typing of punch cards, which we then sent up to London. By the following week, our cards had been returned together with listings saying something like syntax error on line 1.
Yes.
Sometimes the results we wanted. Processing was done on an IBM 7094 at Imperial College, up the road from here. Even then, in 1969, it was obsolete and went offline for 3 months while every single electrolytic capacitor was replaced. I think this was after one exploded. In the meantime, our jobs were run on a CDC 6600 University of London Computer Centre. My very first programme run perfectly, the first attempt. Well, a few times I've been on time and within budget. Even this had an uninitialised variable, and it's been penciled in the initialisation at the top. Anyway, I got hooked on computer programming and decided to do a computer science degree, where I used 1905s and 1904s ICL machines. And by the time end of the course, I'd learned how to punch cards properly in paper tape and type my VU using 2 fingers. After graduating, I got a job at Marconi Elliott Avionics at Rochester, where I worked on compilers, linkers, assemblers, executives, operating systems under Terry Froggatt here today. I'd always wanted to own my own computer, partly to use in my father's business and partly for fun. So when a colleague who was a member of the Amateur Computer Club showed me a copy of the club newsletter offering 2 1301s absolutely free, I was very interested. This was in April '76, and even back then the advert referred to the machine's character and historical significance. I was soon in contact with the guys from Galvor. I was a little disappointed to learn that the machines were actually £150 each, but never mind, their help in dismantling them was worth at least that. I visited Galvor in Surbiton to see what a 1301 was like, and met Stuart Fife and Andy Key. Strangely, my main memories of that meeting are of the surprise that the pet cat was not only allowed into the computer room, but taken up almost permanent residence on top of the power stabiliser rack. And they had had the first electrically flushed toilet that I'd ever seen. I was shown the inside of the CPU and was a little worried when I spotted about the machine speed when I spotted some relays. It was quickly explained that these were only had to work at human speeds, as they merely controlled the manual settings of the values into registers. Both machines were installed on the first floor of the Liverpool Victoria Friendly Society in Southampton Row, again not very far from here. The price of £150 each was arrived at with roughly the scrap value of the platinum in the relays behind the main console. Spares for them were already scarce, and the Friendly Society had bought another pair of machines which had been partly cannibalised as spares already. These were stored in the basement. One came with each of the running machines. The basement was served by a large service lift, but this did not reach the first floor. The passenger lift was big enough for most of the individual units, but not the core store, or shall I say the IS. Fortunately, the unit in the basement has not been cannibalised, although it was not quite as good as the machine's own, as it only had it didn't have a 1900 interface. After a discussion with Stuart, it was decided to cut all the data cables to each of the 5 barn doors, unwrap the power supply cables, unmount the barn doors, and then hacksaw through the frames so it could all fit in the lift. This is a slide of all the wires, the red ones that we had to shot through. So we didn't really, that is about 1/10 of the height. So there's 10 times that amount of wire to be resoldered. We never got around to doing that, and we used the one in the basement. The machine I bought was number 75. It was called Arthur, while its twin in the opposite room was called Samantha. This was bought by another group, and while I and my brother and some friends from work carefully dismantled Arthur into manageable units, it seemed to me that in the other room, despite what they said, Samantha was being scrapped. The ACC June newsletter said that she was being resurrected in rented accommodation in Bletchley. But this is the last I heard of her. Moving Arthur cost more than the machine itself. It was a 150-mile round trip, and I very optimistically thought we might make 2 trips in one day. I hired a large tail lift truck and driver from British Road Services. It arrived 2 hours late. Apparently the previous hire was a pot group who had overrun their hire period. Anyway, we started loading up, and it was half full when the tail lift broke down. We loaded up some smaller items, but as some of the units weighed half a tonne, we decided not to lift them by hand. We were promised another truck would arrive soon, but of course it was another 2 or 3 hours before it did so. We used the new truck's lift as a bridge to transfer the units from the old truck, and then filled the rest of the space and drove home. We finished unloading well after midnight, and as the driver would have exceeded his driving hours, he left his truck at the farm and I drove him home, getting to bed myself around about dawn. It took a bit of persuasion to get my crew of volunteers to do another trip, and I had to promise to use a more reliable company, Dixon's, and this time all went reasonably well. On both trips we had problems with the casters. They're intended really for temporary use just while moving machines, but the spindles was about the only thing on the machine that wasn't designed properly because it was for only a temporary use, and they kept bending and they had a devil of a job with the machine. Similarly, the mag tape unit casters have a plastic tyre on a steel wheel, and after about 15 years old, the hard plastic has got brittle and they broke up. And when you got one flat on a tyre, it's not too bad, you just pass it over. You've got 2 tyres with a flat on each, you have to lift it up about every 2 feet to get it back on its casters. I was still aching the next morning, but full of enthusiasm. I opened the door to the barn where we stored the machine. Couldn't get in the room because it was full of computer units. I got a step ladder, climbed on top, and surveyed what I'd bought, stepping from unit to unit 5 feet up in the air. I did find a small space about 4 feet square and realised what I was dealing with one of those giant kids' puzzles, a giant version of one of the kids' puzzles with plastic tiles you move around in a frame to get a picture. After much shoving, I got one of the units I was going to dismantle for spares next to the door so that I get both sides of it and a gap on the other side. I collected my tools, dropped down into the gap and started dismantling. The 1301 uses a 3-phase electrical supply, but the farm where I live only had a single-phase supply. Indeed, there are only 2 wires to the transformer and the pole in the field. The electricity board wanted, strangely, £1,300 to bring in a 3-phase supply on a series of poles from a different location. It was a ruining of a nice view which put me off this mainly. I looked around for cheap 10 kVA 3-phase generator and eventually found one for £400. It was not ideal, built in 1936, a 3.5 litre cylinder twin hand start diesel. It's extremely heavy. Despite being practically antique, it's actually given very sterling service, both for the 1301 and through the many power cuts and after the great storm of 1987, without mains power for 10 days. The only major problem was the control unit suffered vibrations for the engine. I lengthened the cable and brought the control cable cabinet inside. Naturally, we had a few problems to sort out during recommissioning Arthur. Being new to this type of thing, I thought my trusty Ava meter would suffice. Soon I realised my error. More expense. I bought a second-hand EMI oscilloscope. all valves, but again remarkably reliable. Fortunately, my older brother used to work on valve electronics, and the only time it ever went wrong, he managed to fix it for me. It was just a connection through a chassis that the insulation had broken down. My computer science degree course did contain a section on Boolean arithmetic, some of the theory of logic design, but at computer maintenance I was a complete novice. I could not really even solve it properly. And as for tracing logic faults, I just applied similar principles to debugging software. I learned a great deal very quickly, and I think this indirectly helped my career greatly. A couple of years later, I was pointing out to Marconi's hardware designers how to simplify the connections between a microprocessor and its memory management unit. And he came back later that day and said I'd saved about half the components on the CPU board. A year later, after that, I was designing interface cards for Apple II computers myself, which we sold over 1,000, and other designs followed that. Back in the spring of '77, we had Alpha's basic units powered up, and were running through the prototype test programs published by GEC. We left the MagTape subsystem until later. Amongst the engineering drawings, we'd found a list of links to be removed when fitting a MagTape subsystem to a 1301. We simply made all the links it said to remove. Galdor's own 1301 was originally shipped without MagTape and must have been upgraded quite some time later. You can see the interact connections of the main CPU on the right of a black material, whereas the more modern units on the left are a brown Paxilin. With a little help from my brother and a couple of friends, we were making good progress, considering I had a full-time job. I was looking forward to writing my own software and swapping it with Galdor. When they dropped the bombshell, they were scrapping their 1301 and getting a 1903. They offered me their 1301 and all their accumulated spares, manuals, etc. for £200, which is apparently what they paid for it with. But they paid a lot more for that than the spares. It was very good value, but again it cost me more than that to move it all. It took several weeks, and on the final trip I found they had demolished an internal wall and the remaining units were covered in grey dust. It doesn't seem to have done it any harm at all though. Their machine was originally installed at the University of London, apparently. It was the first one to actually leave ICT. It probably processed my GCE results. That machine was called Flossie, and I've always wondered, as F is the sixth letter of the alphabet, whether the machines were named like hurricanes, starting at A and working on, but it seems not. This has already been talked about. Right, yes. Flossie had also been upgraded in many different ways, including hexadecimal arithmetic. And they had a unique function 28, which added the bottom 6 digits of the memory operand to control register 2, which gives you an indexed addressing mode effectively, which was lacking in the original design, and makes the programs an awful lot simpler. You don't have to write self-modifying code. Flossie had also gained an online keyboard and a direct flexor output console. All this made me decide to dismantle Arthur and install Flessel instead. Logic connections between the racks of 1301s are normally made with wire wrap joints. The main task in recommissioning is wrapping these thousands and thousands of joints. As it's been said before, Galdor soldered all these joints, and when we decommissioned it, we just unsoldered one end. So we needed half the job to do when we put it back together. Being a fairly novice at soldering, we weren't too good at it. We soon realised that you had to start at the top and work down, so that when you dropped the solder onto the wires underneath, you could see it. When we took Arthur apart, when we moved Flossie, the two central CPU racks, we left them bolted together and soldered together because there was enough room to get them out of Galdor and Surbiton and into my place, so they came as a unit. And similarly, Arthur has not been dismantled, so if it ever gets put back together, that will save somebody an awful lot of work. In the middle of moving Flossie, I'd heard from another company with a 1301, which was strangely called 1700 Computer Systems, and was situated in Bristol. The lease in their office had expired, and they had already started dismantling their machine, and had butchered some big bundles of data cables to the line printer, punch card, and that card reader, which should really have been unwrapped at the bottom edge of the CPU. They were desperate for wire wrap tools to get the job done quickly. My mind was wrapped up in moving Flossie, but I wanted to help anyone who might be able to replace Galdor as someone with whom to cooperate on software and spares. I picked up Galdor's wire wrap tools and sent them, and my own, to Bristol. Next thing I heard, they'd gone bust and there was no possibility of getting the tools back. We received a great deal of documentation of the machines. This shows about a third of it. There's a huge, great pile of engineering drawings as well, and a load of manuals. I spent a great deal of time just identifying which parts I needed to read and trying to remember what manuals had what in them so that when the time came I could refer to them. Galdor had made an index to their technical drawings, and I, in the meantime, had made an index to Arthur's. One day I might get around to combining the two indices. The field change notices made interesting reading. Things like strip out the earth connections and replace with half-inch copper braid. And then about 3 months later, strip out the half-inch copper braid and replace with 1-inch copper braid. It obviously had some problems with the voltages down the other end of the machine. When fault finding the hardware, the field engineering manual gets used a great deal. So much so that the edges get frayed and folds wear out and the spine is broken. Time has to be spent repairing the manual before burning the computer. The other constant companion is the address book. Not one of the girls' friends, but one which is every single internal signal connection in the machine, where it comes from, where it goes to, and all the intermediate connections. When working on the machines, you very soon appreciate the very high quality of the engineering. Even the main framework of the machine is incredibly well built. This frame has been scrapped. It stood outside for 20 years, uneven, buried in the soil, but apart from light surface rust, looks nearly as it did when it left the factory. The frames are heavy angle section, welded very accurately, with hundreds of tapped and plain hole drills at very precise locations. Down the centre of the rack runs the space wiring. The high-speed signals run on parallel wires running at least 1/4 inch apart, though it has to be removed. It's not in this unit. I can skip that bit because covered it. And that's flip through a couple of slides. This is the PCB carrier, complete one. This is the close-up of the connections between the racks. The green wires are where it goes off to the next unit and they've all been chopped off. And on the back is the soldering to the wires in the rack itself. There's about 75 connections on there, and there's about 10 of them, so it's an awful lot of connections, and that's on each rack. That's also been covered. That's a close-up of the wire wrap joints connecting the each card into the carrier. Yeah, that's been covered. What was the other thing to talk about is every each oblong pin in the carrier has a wire soldered on, and each of these is a spot of red lacquer to show that it's been tested. When I started to think about the hours which went into making all these soldered joints and then testing each one individually with an avometer, I realised why they cost so much. And when they were new. I think it's a shame that so few survive. Similarly, every single PCB has, on every single soldered joint, has another spot of lacquer to show it's been tested. I don't know if the joints themselves were hand soldered, but many of the older PCBs are plain pack cylinders, no solder resist or anything like that. This red substance you see on covering this one. So I presume slow soldering had not been invented. Many thousands of man-hours must have been used up making just one 1301. The bricks themselves are mind-blowingly simple by modern standards. A single flip-flop occupies a whole board. Admittedly, is a 3-input JK flip-flop with each input separately clocked. It has Q and Q bar outputs, fast and slow, and with the ability to drive a visual indicator on the front panel. The whole board is just staggering by modern standards. This is a double inverter. Oh, sorry, I left out the AND gates. I haven't got a full side of those, but the AND gates are a bit more compact. You've got 4 on one card. There's also, you've got an expanded card with nothing but OA5 diodes on it. As you cannot feed 2 separate wire OR gates from one input, there also has to be a sort of output expander which drives 4 separate OR circuits from one input. And again, there's 4 of these on a card. This is the inverter, and it's actually 2 double inverters on one card. It inverts the signal and re-inverts it for some reason. I don't know why. Probably to slow it down a bit. Again, it's got outputs that drive the visual indicator on the front panel. Back in the war months of '78, I took a week off work, and together with an undergraduate friend, spent a lot of time on Flossy. By the end, we could boot the machine, read in small programs from punch cards and run them. The music programs were our favourites. One of the course door bomb doors didn't work at locations 400 to 799, but fortunately Galdor had fitted a little switch which inverted the high address bit. So he flipped the switch and then words 0 to 1399 worked perfectly, which was enough for our purposes. I think once you get programs which I've been writing on paper into the machine, I had to go out and buy a 026 code punch. It came with a verifier which I immediately scrapped to save space, hoping that some of the parts might be useful for the punch. Although I'd used an 026 before, I never realised it had a big plug board on its left pedestal, nor that it had an input-output socket on the back. These remain a mystery to me. I've been able to find patch cables. I couldn't get another one anywhere, so I had to borrow the one from Arthur. Maybe I'll get around to making new pulleys to suit more modern tooth belts sometime in the future. The ones on electric lawnmowers are around about the right size. With all the peripherals run, we've had all the peripherals running at various times, but never all at the same time. The mag tapes on Flossy are half-inch. They're Ampex TM4. The ones on Arthur are the same, actually. And they run an impressive 75 inches per second. rotor bootstrap loader to load from mag tape, and another to work from paper tape. At various times, various peripherals have been unavailable, so I pretty much could, as long as I had something to read in from, I could get my programs in. Later on, I got the existing electrical supply upgrade to three-phase. Surprisingly, for just £400, they laid all the cable in from about half a mile away on top of the existing poles, put in a brand new transformer. I wrote a high-level assembly for 1301 and had much more planned. The coming of cheap and powerful modern microcomputers made me spend my time where it was more effective. And later I became a director of the company writing software for Apple computers. I got interested in restoring classic cars, and in 1990 Yorkshire Television decided to film Darling Buds of May at my home. So philosophy has been cruelly ignored. A while back I learned of the existence of the Computer Conservation Society, and I contacted Hamish to offer one or both of my 1301s to you. The Science Museum has offered to put one into storage in pieces, but I feel that if they ever need to reassemble it, they will not know how to do it. Or maybe I've admitted to give them some vital component or information that they need. I feel that as I seem to have the only 1301 complete with MagTape subsystem which is anywhere near working condition, at least every part has been assembled since it was last, it's been working since it was last reassembled. I think it really needs to be kept together as a guide to whoever reassembles after. The situation of Bletchley Park has been put on hold on moving him there, so at the present both machines are slowly rusting away in my barn. There's a few more pictures that you might find interesting, let's see. But I've got nothing really more to say.
Just about it.
Yeah. That's
Do we know what might happen at Bletchley then? Are there any plans?
I think it's slightly too early to say. The effort of lugging the beastly thing all this way. It's going to just, it'll just fall onto the floor. We'll have to.
To anyone driving towards London on the A1 in the early hours of September the 22nd, 1962, this van would have been just another vehicle delivering something somewhere. For the ICT driver, it was just the next job on his duty rota. Indeed, for the many people who were concerned with this journey, it was just another job too. Only a small part of a vast undertaking. This film is a record of that job, of how it was planned, carried out, and successfully completed. Many months before, it had been decided that floor space would be taken at the 1962 Business Efficiency Exhibition to be held at Olympia from the 1st to the 10th of October. And as the advertisements were to say, ICT would spread itself. That spread was the decision to have 4 repeat working computers on show on one stand for the first time in the history of the exhibition. This model of the stand illustrates the precision planning required to install 4 powerful computers in a totally unusual location in less than 10 days. Not everything could be shown on this half-inch-to-the-foot model of the proposed 4,000 square foot stand. Certainly not items like the special underfloor air conditioning required to monitor humidity and temperature. Because there's a lot more to it than meets the eye, an accurate model was essential in planning the exhibition, but translating a scale miniature into a full-size stand in less than 10 days was another thing. However, it was achieved. Inside the vast echoing emptiness of Olympia, London, acres of extensive concrete had been subdivided and allocated, and this was ICT's little island, with man-sized cables to bring power to the computers with the king-sized performance. incoming power had to be split up and distributed to every section of the stand, each circuit demanding its own switchgear and protection duties. As the hours marched by, the power conduits were in, the air conditioning plant installed, and all services were securely tucked into the apron. The way was now clear for the contractors to move in to build the stand itself: walls, dividers, panels, and roofs. In the midst of disorderly confusion, the computers had arrived. Component sections were unscrambled, checked off on the plan, and knitted together to form an impressive lineup of computer parts. Because planning of the highest order had been achieved, their commissioning and testing went smoothly forward. As soon as each circuit was through, graduated test programs were run. Programs which had been devised not only to check the functioning of the circuitry, but to isolate and eliminate any bugs which might have crept in during dismantling, transport, and reassembly. On the 29th of September, the installation was complete. The computers had been tested and were in perfect working order, on schedule to the minute, in record time. Further proof, if it were needed, of ICT's planning and teamwork at its best. And then it was Monday, October the 1st, preview day of the Business Efficiency Exhibition, when admission was, in official language, by invitation only. ICT's Deputy Chairman, Mr. Cecil Mead, and Managing Director, Mr. John Bull, welcomed the Lord Mayor of London, Alderman Sir Frederick Hoare, and his party to the stand. The exhibition was visited by over 140,000 during the 9-day run of the show. ICT's chairman, Sir Edward Playfair, in a comprehensive tour of the stand area, saw for himself the company's contribution to this huge shop window of business equipment, and that the range covered every important area of computer technique and application, and at the same time provided the answer to any organization posing the question, how best can we use a computer? One of the features, he must have noticed, was the care which had been taken to provide each computer with a practical demonstration designed to appeal to all kinds of business. He saw, for example, the 558 computer which has been designed to work with the smaller 40-column punch card equipment. One of the demonstrations showed standard costing with comprehensive variance calculations. This computer is visualized for organizations which have already achieved a high degree of mechanization with punch card machines in the 40-column card range. And it can handle the vast majority of commercial processing requirements and make logical decisions where necessary. In keeping with ICT's policy of versatility, the 1101 computer has been provided with 16 input-output channels which can, if required, all be in use at once. The 1101 has a central processor and peripheral devices which are individually buffered, and with the exception of the paper tape reader, all units can be linked for offline working. The computer was set up to demonstrate payroll, piecework, time work, and bonus calculations with analysis of labor costs by department, the preparation of stock market yield tables, and further, under the mnemonic PERT, the control and review of policies and projects by critical path methods made practical by the use of computers. The 1301 demonstrated invoicing, both currency and language-wise, by switching from one language to another in English, Dutch, Italian, French, and German. As a variant, a second demonstration shows the production of renewal notices for vehicle insurance based on the stored underwriting history of each policy. With deft fingertips, an operator sets up the computer on the clearly displayed console. Almost instantaneously, the required data appears on the line printer. At the same time, a typical configuration of the 1500 computer was demonstrating the flexibility of its multiple input, output, and storage facilities. The demonstration showed how stores could be controlled by monitoring stock levels and consumption, forecasting future requirements up to the actual printing of orders on suppliers, and how the continuous expansibility of the 1500 allowed it to take in its stride ever-increasing volumes of store goods. At other times, another demonstration attracted much interest. It was the high-speed analysis of branch sales, where the current performance of each branch was compared and contrasted with the figures for the previous year. Other exhibitors were using ICT machines. For example, boroughs were producing punched cards as a byproduct of a Pneumatic keyboard
That's far enough.